Good afternoon. I'll just get started. So I start from where I left off. Remember, as we said, today our topic is to really understand how to interpret all of the results that are displayed once you have estimated a two-variable model. So we started with the estimated slope coefficient, the intercept coefficient. We talked about the R squared. We touched on the standard error. I'll come back to the standard error. Before I now talk about the statistical properties of OLS regression, the OLS estimators, because that is where the story of standard errors will come from. Let me just point out one thing. There were many questions on multiple R. Multiple R is something that is reported as part of your regular regression results, which I've kind of highlighted in orange on my screen right now. You can see that multiple R is 0.4059. Now, as I told you, multiple R is nothing but the correlation between Y and Y hat, right? And you can see that from the following little exercise that I've done, and I recommend you also do it when you're practicing. The exercise is, remember, the R squared is the squared correlation between Y and Y hat. I showed you that. So when you take square root of the R squared, as I had done in the cell that I've now highlighted in orange, it's nothing but, as you can see, the square root of the R squared. Well, you're just going to get the multiple R. So the multiple R, as you can see, which I have calculated, is exactly what is getting reported, demonstrating to you that always, whenever you run a regression in Excel, Excel always reports it. Whether it is a two-variable regression, whether it's a multiple regression model, multiple R is always the correlation between Y and Y hat. And that's an obvious verdict on your model. A high correlation indicates that your actual dependent variable and the predicted variable are actually moving closely together, which is good news. Okay, right. So now, remember what I told you. We are now going to talk about hypothesis testing. So quickly, I told you that when you have run a model, how good is this model? To understand that, there are three things you have to do. Number one, the slope, the sign and the magnitude of your estimated slope coefficient, especially the slope coefficient, right? Second, its statistical significance. The statistical significance of the variables. That is what I'm going to talk about now, right? And third is R squared. I've already discussed the R squared, okay? So let me talk about the statistical properties of the OLS estimators. So I will just put this on my screen. I'll just run you through my notes. Remember, we are fitting a straight line using the method of ordinary least squares, and the method of ordinary least squares, okay, it actually minimizes the squared values of your residuals. So that is where we started from, okay. So OLS minimizes the value of your squared residuals. So the residuals which are U hat are Y minus Y hat. That is getting minimized in the process of your OLS regression, okay. So starting from there, as we carry on, okay, so the OLS estimators have certain properties, and those properties we can actually classify into algebraic properties and statistical properties. So I have talked about the algebraic properties at length, and these are simply listed over here. So I'll just take you quickly through those. The algebraic properties of our estimators. Again, remember, the estimators are those equations: alpha hat equal to y bar minus beta hat x bar, and beta hat equal to covariance of x and y upon variance of x. Those are the estimators. Those estimators, which together give us our line of best fit, okay, have certain properties. Namely, the sample means of your data will lie on the fitted line. That's one algebraic property. What else is there? The mean of your OLS residuals is 0. That's another algebraic property. Any least squares regression model, whether two variable, whether multiple regression, if it has an intercept, very important. If it has an intercept, you are running unconstrained OLS. Then always the residuals, once you've calculated them, will always have 0 mean. The second algebraic properties of your estimator. Okay, now what else is there? Remember, one of our assumptions is that the errors and the x variables are uncorrelated. Always due to your OLS methodology, the covariance between your x variable and the residuals will be 0. That is coming out of the way the line of best fit is actually estimated. And again, as I had mentioned to you, you will see that the sample means of the actual and estimated values are equal, so that both y and y hat, right, they have the same mean, which is y bar. That is another algebraic property. Uh, the sample covariance between the predicted values and the residuals are 0. So you see the y is being split into these two parts, a part which is the explained part of your model, y hat, and the part which is not explained, or the residuals. And explained and the unexplained models are uncorrelated. Sample covariance between the two of them is 0. So all of these are very simple algebraic properties which you can check with some actual data set using Excel. And I would really encourage you to do so to clarify ideas, understanding of the simple two variable model. Okay, all right. Now, what are we going to do? We are now going to look at some of the statistical properties of the estimators. So here they are. Here are our estimators: alpha hat, which is y bar minus beta hat x bar, and beta hat, which is this covariance of x and y upon the variance of x. These have certain statistical properties which flow from the fact that alpha hat and beta hat are random variables. Okay. Now, very important, where is this coming from? It is coming from the very, very first statement that we made regarding our OLS model. What was that? That we have a model which is linear in parameters, and the model is dealing with y, which is an observable random variable, x, which is also an observable random variable, and u, which is an unobservable random variable. Now look at alpha hat and beta hat on your screen. So basic fact of life again is that function of a random variable is also a random variable. Okay. So alpha hat and beta hat, which are our estimators, are functions, as you can see on the screen, of y and x, which are random variables. They are also random variables. So as I said, this is at the heart of understanding the statistical properties of the OLS estimators, which are called formally Gauss-Markov Theorem. So a statement of the statistical properties of the OLS estimators is known as the Gauss-Markov Theorem. Okay. And what does the Gauss-Markov Theorem say? So the Gauss-Markov Theorem says that alpha hat and beta hat are pretty cool. Okay, they are blue. And let's take that blue apart, because blue, as you can see, is an acronym. They are best, they are linear, and they are unbiased. So that's the BLU. And E, well, the E is they are estimators. Okay. So the Gauss-Markov theorem, I repeat, is essentially nothing but a statement of the statistical properties of your OLS estimators. All right. Okay. So let's now kind of quickly unravel this. All right. Now, you see, to appreciate the statistical properties, you'll have to remind yourself about the basic thing about random variables. And for that, I thought maybe it's a good idea to quickly have a look at the probability distribution of a random variable. Okay. So very quickly, remember random variables are broadly of two types. You can either have discrete random variables or you have continuous random variables. So we are going to talk about continuous random variables, where continuous random variables can take any number of values in a certain range. Okay. So continuous random variables follow certain probability distributions. And that probability distribution of a continuous random variable is characterized by what we call a density function. Okay. So probability density is what captures the probability distribution of a continuous random variable. All right. Why am I saying this? You see, these properties, this based, linear, unbiased, all of these properties have to be understood in terms of the characteristics of the probability distributions of our random variables. Which are our random variables? Alpha hat and beta hat. So you see, the Gauss-Markov theorem is essentially telling you about what are the probability. They're telling about the probability distribution of alpha hat and the probability distribution of beta hat. Okay. So before we proceed to understand what these things are, I quickly want to show you a probability density. But before that, we can actually do something better. Let us just draw a probability density. So you see, I have a certain principle in life. Okay, what is that? If you are drawing a diagram, label the axis. I just do that as a matter of principle. Always label axis when you are drawing diagrams. Now here, let me just tell you that if you are a teacher, I mean many of you here may be teachers, you know, students follow us. Whatever we do, they may not say, but they copy us. I have seen that. So as a teacher, when you're drawing diagrams online or on a blackboard, if you always label axis, your students will always label axis. So think of the joy when you are correcting their exam scripts. You will actually see diagrams with the labels, with the axis label. Okay, all right. So let us see what we put on the axis when we are plotting the probability density of a continuous random variable. In this case, let me take the probability density of beta hat. Okay. So what am I plotting on the y-axis? I'm plotting the various values that beta hat can take, the various values. And what am I plotting on the y-axis? On the y-axis, I'm plotting the density of beta hat. So the density function is normally written like this. So f of beta hat simply gives the probability density of beta hat. Okay. Now, what do we know about the probability density of beta hat? Remember, I told you that the hero of the piece is the error term. What have we assumed about the error? That the errors are normally distributed. Correct? Which means y. Think of your regression model. Y is equal to alpha plus beta x. So so y is equal to alpha plus beta x plus u. Now we have assumed that the error u is normally distributed. And what is the mean of the errors? 0. What is its variance? Variance is constant. It is sigma squared. Correct? I have done this. Now, normal distributions have a property that linear combinations of normally distributed random variables are also normal. So because u has a normal distribution, guess what y has? Y is a function of u. Y also has a normal distribution. So y is also normally distributed. What is the mean of y? Well, the mean of y is a function of x. So mean of y is alpha plus beta x. Right? The expected value of y given x is equal to alpha plus beta x. Why? Because the expected value of the errors is 0. Correct? And what is the variance of y? The variance of y is of course also sigma square. Because the random part of y is essentially being driven by u. So it is the error variance and the variance of y which are really the same things. Now, having said that, so errors are normally distributed, because of which y is also normally distributed. Okay. Now, how are we proceeding to calculate alpha hat and beta hat? We are using these formulae. Equal to y bar, this is equal to covariance of x and y. So basically functions of y, alpha hat and beta hat are basically functions of y. Now what about the x's? You see the x's, we are conditioning on the x's, which means we are treating the x's as though they were constant. So the distribution of alpha hat and beta hat is driven by the distribution of y, which is driven by the distribution of errors. So what is the bottom line? The bottom line is that alpha hat and beta hat are also normally distributed. Okay. Okay. So let me just repeat that once. So we said that, look, alpha hat and beta hat are random variables, which means they have probability distributions. And we have assumed that the errors are normally distributed, because of which y by assumption is normally distributed, which is what makes alpha hat and beta hat, which are nothing but functions of the y's. Okay, so which makes alpha hat and beta hat, okay, functions of the y's, also normally distributed. So now, if I'm going to talk about the if I'm now going to talk about the probability distribution of alpha hat and beta hat, what would it look like? It would be normal. Okay. Now I hope all of you know what a normal distribution looks like. It is symmetric. So the normal distribution is symmetric around the mean. Okay. All right. So let me just plot that so that you're able to see it very clearly. Okay. So so here, yeah. Yeah. So here we go. I'm plotting the probability distribution of beta hat. I have varied values on the x-axis. I have the density of beta hat on the y-axis, and I know that the density is normal. So here you go. This is a normal. Yeah, it doesn't look very normal. I'm sorry, but okay. So let me try once again. Please assume that this is okay, better. Okay, so this is a normal distribution. Okay, I'm just sort of freehand drawing it. Okay, right. Now, so this is symmetric around the mean. So now the question is, where is the mean of beta hat? That's the first statistical property of your OLS estimators. So remember I said that according to our Gauss-Markov theorem, the OLS estimators are blue. Okay. Now we have already seen that the OLS estimators are linear combinations of the x's and y's, the linear combinations of the y's. Okay, it's a linear function of the y's. That's the linear bit. Now we are being told, that's the result, it can be proved, that if all the OLS assumptions hold true, then the OLS estimators are actually unbiased. What does that mean? It means that the mean of beta hat is at beta. Okay, the expected value. Remember, a random variable's mean is also its expected value. So the expected value of beta hat is equal to beta. Now, if you remember in our Q&A sessions prior to this session, I had distinguished between beta hat, which is a random variable, and beta, which is a unknown constant. So beta is this relation, is the slope of the relation between wage and education that we were trying to estimate, which we did not know. So it is a number, okay? It's a number that we do not know. Please remember that. Now, if all the OLS assumptions hold, then the Gauss-Markov theorem is telling you something beautiful. It is telling you that, look, if you're using the OLS estimators and if all the assumptions hold, then the center of the distribution, probability distribution of beta hat is actually at beta. Even if you don't know what is beta, you're still using an estimator which is centered at beta. Okay, all right. Now to understand unbiased, the best thing is to look at bias. All right. So what I'm going to now show you is a picture of a biased estimator that will help you understand unbiased more clearly. Let's have a look at what a biased estimator can actually look like. Okay. So right. So hang on. Okay. Yeah. So on my screen, right, what I have is the picture of a biased estimator. So let me start with the axis. All right. So here I am measuring a random variable called W. Okay. Now this variable, this random variable W takes many kind of different values, so that I can actually be talking about two random variables right away. So I'm talking about one random variable W1 and another random variable W2. So I have two density functions. So all the variate values, W1 takes many values, they are all measured along the x-axis. W2 also takes many values, so W2 also takes many values, these are also measured along the x-axis. Okay. Now what am I measuring along the y-axis? I am measuring the densities. I am measuring the densities of W1 and of W2. These two random variables that I am now talking about. Right. Now, what are these random variables being used for? Just like we are using beta hat to estimate the unknown parameter beta, W1 and W2 are two alternative estimators for one unknown parameter called theta. So there is some unknown population parameter. The population, as you know, is the entirety of the event that is being, the entirety of the variable that is being talked about. In my wage education model, the population of wages is the wages that are earned by all the people. Right? That's a population, and we are working with a sample. So populations have this parameters. In our example, there is a relation between all the wages and all the people with their educations, which is characterized by a straight line that we don't know. Alpha, beta, these are unknowns. So similarly, theta in a different context is another unknown. And I have two random variables, two estimators for theta, W1 and W2. Okay. Now look, both of the estimators have very similar distributions. They're both symmetric. PDF is another word for probability density function. So this is the PDF of the estimator W1 and this is the PDF of the estimator W2. Now let's look at the means of these two estimators. Okay, where is the mean of W2? This is the mean of W2. It is written over here as the expected value of W2. Right. So here you go. So the expected value of W2 is giving you the mean of the estimated W2. And what about the mean of the estimated W1? The mean of the estimated W1 is given to you right over here. Now, what is this value? What is the mean of W1 giving you? The mean of W1 lies on theta. That is, so theta is just a number. And remember, I don't know what is theta. I'm estimating theta. So I'm proposing two estimators. One is W1 and the other is W2, right? And I see that W1 is unbiased. Why? Because the mean of W1 is on theta. But what about W2? The mean of W2 is much more than theta. So I will just show this to you once again. So please look at this diagram very carefully, because conceptually this is something very important. What are we trying to do? We are trying to understand what it means to talk about the statistical properties of estimators. We are trying to understand what we mean when we say that the OLS estimators are unbiased, right? To do that, we are taking an example of two different estimators of a single population parameter theta. Estimators are random variables, which means they have probability densities. So here you see the probability density of W1, which is one proposed estimator of theta, and of W2, which is the second proposed estimator of theta. Okay. Now you see that the mean of W1 is exactly equal to theta, but the mean of W2 is greater than theta, right? The mean of W2 lies over here. So you see, if you use W2 to estimate theta, you will get a positive bias. What does that mean? It means you will tend to return estimates that are higher. So somebody here was talking about, can I use the data to estimate COVID rates? Yeah, sure. Suppose I am using a sample, right, to estimate average, the average incidence rate of COVID. And I'm using W2 instead of W1. So in this case, my population mean is theta. Okay. So I'm saying that, look, actually the incidence rate theta, which I do not see, is what I'm going to try and estimate. So if I'm using W2, I will give you an estimate. I'll give you a number based on my sample, which is way higher. So the incidence rate will be much higher than what it actually is, because actual rate is theta. But if you were to use W1, then W1 would give you an unbiased estimate. W1, Abha, please turn off your audio.
Okay,
Abha,
okay,
yeah.
okay, I'll do that.
So basically, uh, yeah. So basically, if you're using W1, then you're going to get an unbiased estimate of theta. Okay. So I hope you understand what unbiasedness means. To take you back to my OLS regression, please realize that the first of my Gauss-Markov results, which is given that beta hat is a linear combination of the y's, beta hat being unbiased essentially means that the center of the distribution of probability distribution of beta hat actually lies at beta. Now, beta hat has a normal distribution. Pardon my bad drawing, but this is normal distribution. Okay, so this is normally distributed. So the distribution of beta hat is normal, where the mean of the distribution is beta. Now, because beta hat is random variable, so it will also have some variance. That's with the, probability distributions, probability densities have means, they have variances. These are moments of the distribution. So these are basic things you have to understand, right? So the variance of the distribution is of course given by this spread. All right. So unbiasedness essentially is a property of the means of the distribution. Alpha hat is also unbiased. So alpha hat also follows a normal distribution. Mean of alpha hat is alpha, and it has a certain variance, which is the variance of alpha hat. Okay, right. Now so we are done with E. E is estimator. U is unbiased. L is linear. They are linear combinations of the y's. Now let's come to best. What is the best part is the best, right? What is the best part? The best is that these are efficient. Okay. What are efficient estimators? Let me take you back to my PowerPoint slide and show you a picture of a efficient estimator. Basically, efficiency is a property of unbiased estimators. So a basic minimum property that you want from your OLS regression is that the estimators have to be unbiased, which means they have to be centered around on the unknown parameter you're setting out to estimate. So I love this actually. I mean, look at the beauty of the whole thing. What is alpha beta? Nobody knows, right? So, so that's the starting point. Nobody has seen alpha beta, right? But when you're using OLS estimators, you can claim Gauss and Markov. Gauss is a very famous statistician, passed away a long time ago, German statistician. Gaussian distribution is a normal distribution. So Gauss and Markov has actually proven to you that alpha hat and beta hat, your OLS estimators are centered on alpha and beta, which nobody has seen. Wow, beauty. I mean, that's a beauty, right? Okay, so let us see what an efficient estimator is, where I just told you that efficiency is a property of unbiased estimators. Okay, right. So let me just take you down to, yeah. So let me just take you to the next slide. Yeah. So here again, you're looking at two estimators, W1 and W2. W1 is an estimator, W2 is another estimator of the unknown parameter theta. Both of them are unbiased, as you can see, right? The mean of W1 and the mean of W2 are both centered on theta. So I'll just clear the ink and you can have a good look. See that W1, W2 are both unbiased. And remember, efficiency is a property of unbiased estimators. First unbiased, then efficiency. Now, guess which one is more efficient? W1. Why? It has lower variance. So look at what we are trying to do. We are trying to estimate theta, correct? And we haven't seen theta, but we are using an estimator which is unbiased, which is centered on theta. So depending on our sample, our estimators could take us far from theta, or it could keep us close to theta. We don't know because we don't see what is theta. But if I had a choice, I would never use W2. Why not? Because you see, W2 can take me very far from theta. Theta is fixed. Theta is here. But the actual estimate that I will report could either be theta hat 1 or it could be theta hat 2. Now, suppose I'm using estimator W1. So let me erase this. Suppose I'm using W1 to estimate theta. What is the probability that I am going to get an estimate theta hat 1? What kind of an estimate is it? Not a very nice estimate. Why? Because see how far it is from theta. It's quite an overestimate. So I ideally want a sample which will give me a some sort of estimate which is close to theta, right? Now the probability that I'm going to get so the probability that I'm going to get an estimate like theta hat 1 when I'm using W1 is pretty low. So remember, what is probability in a density? It is area under the curve. So this bit is the probability if I'm using W1. But what about the probability when I am using W2? So if I'm using W2, right, look at the probability. The probability is this whole blue area, much more. Do you see? The probability of getting a estimate that is quite far away from theta is much lower when you are taking an efficient estimator which has lower variance. So efficiency is essentially a feature of the variance of your estimator. And that's where the best comes in. In the class of all linear, unbiased estimators of alpha and beta, OLS estimators have the least variance, which is why they are best. So best means they are most efficient. Most efficient means that they have least variance. They have least variance in the class of all linear and unbiased estimators of alpha. And what you see on your screen demonstrates what it means visually to have an inefficient estimator, where W2 is an inefficient estimator compared to W1, right? So W1 is a efficient estimator because it has much less variance, and W2 has this much greater variance, where again, please note, both of them are unbiased. Both of them are centered on theta. Okay, right. So let us get back to what we are essentially discussing. We are essentially discussing the statistical properties of the OLS estimators, which we have to do. Without that, we cannot talk about standard errors. All right. So we first said that, look, alpha hat and beta hat are random variables. We realize therefore that they have probability densities, and the Gauss-Markov theorem tells you that these are best linear unbiased estimators, which are properties of the estimators linked to the mean and the variance respectively of the probability distributions of alpha hat and beta hat, right? Very quickly to remind you, alpha hat and beta hat are precisely these estimators that you are seeing on your screen. So please keep them in your head, okay? This is alpha hat and this is beta hat, okay? All right. So now let us continue with the statistical properties. Right. Now, I can actually show you this, right? I can actually show that beta hat follows a normal distribution with mean beta and a certain variance. And alpha hat follows also a normal distribution following from our assumption with mean alpha and a certain variance. All right. Now, I'm not showing this to you actually because we don't have the time, but any standard textbook such as Woolridge will in an appendix derive for the two variable model the mean, the variance and the properties of the OLS estimators. I recommend that you read this, okay? And that's exactly where all of this is coming from. So I can show that the variance of beta is actually this. The variance of beta is sigma square upon sigma xi minus x bar whole square in the two variable model. Okay. What is sigma square? Sigma square is the error variance. Do I know that? No, I don't know that. Which means what? Which means I don't know the variance of beta hat. Right? Beta hat, the variance of beta hat is a function of sigma square. Similarly, if you look at the variance of alpha hat, the variance of alpha hat is also the function of sigma square. So let me just delete all this. Just look at the variance of beta hat. It is a function of sigma square, which is an unknown, and these are of course known. Look at the variance of alpha hat. The variance of alpha hat is a function of sigma square, which is an unknown, and it is a function of the knowns. So how do I now calculate the variance of alpha hat and beta hat? I can't do that. I can't do that until first I have estimated sigma square. So I first have to get sigma hat square. So to estimate variance of alpha hat and beta hat, we need an estimate of sigma square. That is the first thing that you have to realize as we inch our way towards an understanding of standard errors and hypotheses. Okay, all right. So let us have a look at what is going on. Now, how do I estimate the disturbance variance sigma square? Okay, that is the next question, because without that we cannot estimate the variance of beta hat and the variance of alpha hat. Now, as you can see, we have used the least squares residuals to proxy the errors. So the residual variance, so remember errors are u, residuals are u hat. We saw them all morning, right? We saw the residuals in the morning. So the variance of the residuals should work as an estimate for the error variance. So the variance of residuals should ideally be this particular term that you see here. Except there is a problem here. Okay. The variance of u hat, this particular, so you see what is the problem here is the variance of u hat in this form turns out to be a biased estimator of sigma square. So we are not bothered about that. Bias hai, koi baat nahi. We will get rid of the bias. How will we get rid of the bias? Very simply. I'll just show you how to get rid of the bias. Okay. So we just have to divide the residual sum of squares by the degrees of freedom of the regression. Okay. So here you're asking me, what is the degrees of freedom of the regression? Okay, let me quickly just tell you that in the two variable model, okay, where we have two unknown parameters which are being estimated, okay, and we have n observations. So we have n number of observations. We actually have 526 observations, okay, in our data set, right? And we are only estimating two unknown parameters. What are they? Alpha and beta. So the degrees of freedom is the total number of observations n minus the number of unknown parameters that are being estimated. So 526 minus 2, 524 is the degrees of freedom of my regression in the data. And in general, we define degrees of freedom as the number of observations minus the number of unknown parameters being estimated. Okay, so if you take the residual sum of squares, which mind you is actually the residual variance because the residuals have zero mean, and if you divide that by the degrees of freedom, wow, what do you get? You get an unbiased estimator of sigma hat square. Okay. So remember, estimators are all random variables. So this is also one random variable. The residual square is also a random variable. It is a function of x and y. So remember, u hat is equal to y minus y hat. Y hat is alpha hat plus beta hat x. So u hat is also random, right? Okay, so my message for all those who who have a problem with random variables, you see, if you want to do regression, you have to love them. Learn to love random variables, okay? Then they will reveal themselves to you. They will show their distributions and all of that. Believe me, I have learned it that way. Once I started loving my random variables, I started understanding them. I mean, look at people around us. I mean, how do you understand friends? I think you start by loving your friends and then you start understanding. So you have to get friendly with random variables. And there's so many, you know, that we just have to live with them. That's my message to all of you who think random variables are problematic. Okay, so we are trying to understand how to estimate sigma square. Why are we suddenly doing that on a hot afternoon like this? We are doing that because we just realize without that there is just no go. Without an estimate for sigma square, there's no way I'm going to get an estimate for var beta hat and var alpha hat. And what do I find? I find that there is a pretty neat solution. All you need to do is take your residuals, you just square the residuals, you just add them up, and what you have is so you take the residual, you add them up, you square them, you divide them by the degrees of freedom of your regression, and you have an unbiased estimator of sigma hat square, which is so sigma hat square is equal to sorry. All right. So this is sigma hat square. It's already in a box, right? So sigma hat square is just your residual sum of square divided by the degrees of freedom, and it's unbiased because its expected value is equal to sigma square. So it does the job. Okay. Now what do we see? So once we replace sigma square by sigma hat square in the expressions of var alpha hat and var beta hat, we get estimated variances of, we get the estimated variances of beta hat and alpha hat. And positive square root of these estimated variance give us the standard errors of the estimators of beta hat and alpha hat. Ooh, is that too many random variables and too many estimators and too many standard deviations? Okay, I get you. Let's cut to some data. Let's cut to some data. Here you go. Here you are. Okay. Right. So what is it that we are talking about? We are talking about some data. First thing, okay? We are talking about some data on a dependent variable wage and an explanatory variable education. And then we use this data and we run a regression. And here is the regression output for you. Today morning, we looked at the slope and the intercept. We looked at the R squared. We looked at the multiple R squared, and all of that stuff we have looked at, right? Now, it is time to talk about standard errors. So what have we just been seeing? We've been seeing that, look, there is an estimator for your sigma square. What is the sigma square? It is your whole stochastic unknown error variance, right? Now, because it is unknown, we estimate it. How do we estimate it? We estimate it using sigma hat square. What is that? Sigma hat square is nothing but sum of the squared residuals. Morning, I showed you the residuals. I generated the residuals. They're right here. They're right here. Here are the residuals. So you square the residuals and you divide it by the degrees of freedom of your regression. Degrees of freedom being n, which is the number of observations, minus the number of unknown parameters, which is 2. So look, I have okay, so if you see, I have 526 observations and I'm just estimating 2 unknown parameters. So the degrees of freedom of my regression is actually 524. Okay, n minus 2. All right, it is something that's coming up right here. So when I take my residuals, I square them and I add them and I divide it by the degrees of freedom of my regression, I will get an estimate of the error variance. I'll get an estimate of sigma square. So once again, sigma square is hatless. No hat. It is the unknown variance that you do not see. Okay? And sigma hat square is what you estimate once you have the data. And once you take the positive square root of sigma hat square, guess what you get? The positive square root of sigma hat square is sigma hat. And what is sigma hat? It is the standard error of your regression. Understood? So this thing which is in red over here, hang on. So this thing which is in red over here. So the only thing in red, as you can see over here, all right, is this bit over here. What is that? That is the standard error of your regression, right? What is that? That is sigma hat. Again, what is sigma hat? Sigma hat is nothing but an estimate of sigma. And what is sigma? Sigma is nothing but the unobserved standard deviation of the errors. So you are wondering, so when it comes to sigma, it is standard deviation. But when it comes to sigma hat, it is standard error. Why? Because sigma is standard deviation. It is the under root of a variance. But what is sigma hat? Sigma hat is under root of an estimated variance. Okay? Loosely, that is the reason it's called a standard error and not a standard deviation. Clear? Okay, now wake up to the fact that we have other things to deal with, other standard errors to deal with. And look at this. What is that? So remember, alpha hat and beta hat are also what? Random variables. Because they are random variables, they have means and variances. Means were, they are unbiased, so the means were equal to alpha and beta. Khatam. What about the variances? The variances were functions of alpha, sigma square. So the mean of, so the variance of beta hat and the variance of alpha hat are all functions of sigma square. Correct? Right? So we saw that. And then we said, hi, kya kare? Sigma square dekha nahi. So then we learned how to estimate sigma square. The minute we estimated sigma square, we also got an estimate of the variance of beta hat. So you see this big hat over here, this big hat thing. This is the estimated variance of beta hat. Why estimated? Because initially I did not know it because it was a function of sigma square. Okay? Now look, once I take the positive square root of the estimated variance, what I get is the standard error of beta hat. Theek? That is what this is. This is the standard error of beta hat. Silence. Yeah, we've done quite a bit. Okay. So basically, what have we done? Basically, let me tell you what we have done. All right. We have covered a lot of ground. Let me get rid of all these annotations. So we said that, look, I want to understand how good are my results once I run a regression model. I started with that, correct? Then I said that, look, to understand it, first you need to look at the sign and the magnitude of your coefficients. Finish. Then we need to look at the R squared. Finish. Then I said you have to look at statistical significance. But we saw that to get to statistical significance, which is over here, from here you have to encounter standard errors. They are sitting in the middle. You can't jump from coefficients to t-stats without understanding standard errors. So that is what we have done. We have taken the plunge. we have understood what are standard errors, right? So the understanding followed a long sequence. The understanding followed the sequence that first, x and y being random variables, alpha hat and beta hat, which are estimators of alpha beta, are also random variables. Because they're random variables, they have a probability distribution. That probability distribution has a mean, has a variance. Now, what kind of means and variances? The Gauss-Markov theorem tells you something about it. It tells you alpha hat and beta hat are blue. They are best, linear, unbiased estimators. In the class of all linear and unbiased estimators of alpha and beta, okay, alpha hat and beta hat are number one unbiased, so they are centered, the distributions are centered on alpha and beta respectively, and they have minimum variance in the class of all linear and unbiased estimators of alpha and beta. So they are blue. We understood that also. Having done that, what did we do next? We said that, okay, so alpha hat and beta hat are random variables. So they have means, they have variances. The means are alpha and beta. Achha. So what were the variances? We saw that the variances are functions of sigma square. So what is sigma square? Sigma square is our error variance. It's the homoscedastic error variance. So then we ran into a problem. Ki alpha hat and beta hat, the variances of that I don't know because I don't know sigma square. So quickly we solved that problem. We said, koi baat nahi. You have the residuals and the residuals are estimating your errors. Okay. So we are going to simply use the residual variance to estimate the error variance. Now there also we ran into a problem. We saw that if you divide by n, the residual variance is giving a bias. ठीक है, कोई problem नहीं. So we divided by n minus 2. We divided by the degrees of freedom of the regression. When you divide the residual variance by the degrees of freedom of the regression, what you get is an unbiased estimator of sigma square. We call that sigma hat square. All of you who are listening to me, let me give you a task. Take some data, any data set, generate the residuals, okay? Generate the residual sum of squares. Take the sum of squared residuals, divide by the degrees of freedom of the regression, 524 in this case, and then check that you get square of the standard error of the regression. Because what is the standard error of the regression? It is nothing but sigma hat. It is under root of sigma hat square. Number one. Number two. Remember where we started out from? We started out from the fact that, look, variance of alpha hat and variance of beta hat are functions of sigma square. The minute you have sigma hat square, what do you have? You have an estimate of the variance of alpha hat and the variance of beta hat. You have that estimate. And once you take under root of that estimated variance, what you have is the standard error of beta hat. So if you remember in the previous screen, I had showed you that beta hat is normally distributed with mean beta and with a certain variance, which is the variance of beta hat. I showed you that, correct? Now, you see, so look. Now, when you are looking at the standard error of beta hat, when you're looking at this, what are you seeing? You are seeing an estimate of the standard deviation of beta hat. Why are we not calling it the standard deviation? Why are we calling it standard error? Because it is the standard deviation. It is the square root. It is the positive square root of an estimated standard deviation. Estimated variance. Okay. So I hope you will keep this very clearly in your mind. That standard error of alpha hat and beta hat are nothing but estimates of their standard deviations. Okay? Cool? Right. So having understood these three standard errors, which play a very important role. So this is sigma hat, right? The standard error of your regression, which is the standard deviation, estimated standard deviation of the errors. And these, which are standard deviation, estimated standard deviations of your alpha hat and beta hat, play a very important role in hypothesis testing. So what is hypothesis testing? Let us do a bit of theory on hypothesis testing. Now, I know you have questions. I will take some questions in the last bit of the session, and accumulate your questions, because I'm going to be back tomorrow. So even if I'm not able to answer all the questions today, I will certainly answer them tomorrow. So please plug away, chat away, and put your questions on the chat. I will surely have a look at all of them, and I will be answering them. If not all of them today, certainly tomorrow. Okay? And I will now continue, and I will talk about hypothesis tests. First, the theory of hypothesis tests, and then how to do it. Okay? And I will be doing that in the context of this two variable model. I will be doing that in the context of this particular example that I'm using with you. Okay. All right. So let me get back to some theory. Okay. Now, I think all of you have been attending this session, which has been taking you through various kinds of hypothesis tests. And hypothesis tests in the two variable model, in the regression model, is essentially exactly the same in principle. You always test hypothesis about population parameters. Now, in this case, what is our population model? My model, just to remind you, is y is equal to alpha plus beta x plus u, where y is an observable random variable, x is an observable random variable, and u is an unobservable random variable. So they are all random variables. What is alpha and beta? Alpha is a unknown parameter, so is beta. So what shall we test hypothesis about? Obviously, we're going to test hypothesis about the unknown parameters. So I will write down my model once again. My model is y is equal to alpha plus beta x plus u, and I'm going to test the null hypothesis that beta is equal to 0. And my alternate will be that beta is not equal to 0. Now please look at this null and alternate. They are very important. Why? Because you see, suppose beta is equal to 0. If beta is equal to 0, then what does that mean? It means y is equal to alpha. It means x has no role in y. In my example, it means that education has nothing to do with wages. So very bad news, right? So as a researcher, one of the most important hypotheses that we want to test is my slope coefficient non-zero? Because until and unless your slope coefficient is non-zero, you don't have a story. You can't say how y changes with changes in x, correct? So this is a very important null hypothesis that we want to test. Now, how are we going to test this null hypothesis? We are going to test this null hypothesis using this particular random variable. Okay, again a random variable. As I said, you have to love them. So look, remember, beta hat is a random variable, and one of the basic principles of life, functions of a random variable is also a random variable. So this particular term which I've circled, beta hat minus beta upon the standard error of beta hat, is a function of beta hat. And because it is a function of beta hat, it depends on beta hat, it's also a random variable. Now, remember, the beta hats are normally distributed. We can say that. The beta hats are normally distributed with mean beta and with some variance. Because of that, this particular character, beta hat minus beta upon standard error of beta hat, follows a t distribution. It follows a t distribution with the same number of degrees of freedom as the regression. Okay, so the degrees of freedom is n minus k minus 1. What is k? K is the number of explanatory variables, and the 1 is for your constant term. Okay, so don't get confused. K is simply telling you that there are say k number of explanatory variables. In my model, there is one explanatory variable, so k is 1. And 1, the other minus 1 here is for the constant. Okay. Right. So I will just repeat this once again. When you want to test the null hypothesis that beta is equal to 0, right, against the alternate that beta is not equal to 0, you will be using this particular random variable. And this particular random variable has a t distribution which has the same number of degrees of freedom as your regression. Okay, so the degrees of freedom of the t statistic in this case is going to be 524. Okay, now how do I proceed with the hypothesis test? With the hypothesis test, I proceed by assuming the null is true. Right? Now, when I assume my null is true, look what is happening to this. If the null is true, then what is happening to beta? Beta is equal to 0. Then what does this become? The t statistic simply becomes beta hat upon the standard error of beta hat. Now, these are a few conceptual points which I want you to understand very clearly. Okay? First of all, what is my model? My model is equal to alpha plus beta x plus u. Y is equal to alpha plus beta x plus u. In this model which I'm circling, what do I want to test a hypothesis about? Obviously about something I don't know. What don't I know? I don't know what are the unknown parameters. I don't know what is beta. So always the hypothesis is about the unknown parameter. Never is a hypothesis about beta hat. Please get this clear, okay? Never test a hypothesis about beta hat. Beta hat is a random variable. It's a estimator. So that's the first point. Always the hypothesis is about beta. And a very important hypothesis is beta is equal to 0. We want to test it because until and unless we are able to reject this null hypothesis, we don't have a good model at all. Okay. How will we do this test? We will do this test using a random variable which follows a t distribution. T distribution, where is it coming from? It's coming from the normally distributed errors, because of which the beta hats have normal distributions, because of which this particular thing has a t distribution with as many degrees of freedom as your regression, where the degrees of freedom of your regression is equal to total number of observations minus number of explanatory variables minus 1 for the constant term. Okay, that is the first thing. So having said all of this, how do we proceed to do the hypothesis test? We proceed by assuming the null is true. And when the null is true, our test statistic, so the one that I'm pointing to, the test statistic takes the value beta hat upon its standard error. What is beta hat? In our model, beta hat is 0.54 and the standard error has already been reported, right? So once you divide beta hat by its standard error, you will get the t statistic, as you can see right now over here. So once I am over here, you can see that when I divide the beta hat, which is 0.54, and I divide it by the standard error of beta hat, which is 10 point something, what do I, sorry, that was a mistake. When I divide it by its standard error, which is here, which is 0.05 something, what do I get? I get the, so I've highlighted in orange, I get the t statistic. Okay. All right. Now, so I hope you see now why I've been boring you to death talking about standard errors. Standard errors are very, very useful. Standard errors help to calculate the t value or the t statistic, which will help you do a hypothesis test that beta is equal to 0. Now, how do we do hypothesis tests? We do hypothesis tests by working on the t distribution. I will just show it to you in a minute, but let me just tell you that when we have a very high value of the t statistic, what is high? So you see, as long as we have values that are, lying above, a cutoff of 1.98, let's say values higher than 2. So values like 3, 4, 5, these are all very high values of t statistics, which means these values lie out in the tails. Now, in this course, you have done hypothesis tests. So you have seen how to reject a hypothesis. You reject a hypothesis when the calculated value of your test statistic lies in the tails, or it lies in the critical region. Now, high values of the t statistic lie in the tails, it lies in the critical region, leading to a rejection of the null hypothesis that beta is equal to 0, as in this case. So in this case, you saw how I derived the t-stat, right? The t-stat is nothing but beta hat divided by its standard error. Similarly, you should check that the t-stat for alpha hat is nothing but alpha hat divided by its standard error. Both these t-stats are going to be used to test the hypothesis that alpha and beta are equal to 0. In this case, it is very interesting to see that I'm rejecting the null that beta is equal to 0, but I cannot reject the null that alpha is equal to 0. Okay, so the t-stat for beta hat is 10. That's very high. It lies in the tails, leading to a rejection of the null hypothesis that beta is equal to 0. But the t-stat for alpha hat is almost 0. Okay. Sorry, it is very small, right? It is just minus 1.32, right? So basically, this is telling me that it does not lie in the critical region, and I cannot reject the null hypothesis that alpha is equal to. Okay. Okay. So, right. So, look, um, uh, there are other ways of doing hypothesis tests using p-values, and this is something that I'm going to start with from tomorrow. Okay, so right now let me just call it a day here. Okay, so we've understood how to interpret coefficients in a two-variable model. We have understood the very important point of standard errors and how to use them for hypothesis test. Let me just tell you that when as in this case, when you're rejecting the null that beta is equal to 0, you say that your results are statistically significant. Education is statistically significant in explaining the variation in wages. Okay, so we've learned about statistical significance using p-values. Okay, so I think very important groundwork has been done today. And I would like all of you to actually revise these concepts so that tomorrow, when I take you through various kinds of models which are multiple regression models, models which have different functional forms, I will really take these entirely for granted, and we will be proceeding faster. So don't worry about the fact that we may not have been able to cover the basics of multiple regression interpretation, etc. Really, those are very, very easy compared to what we've done today, which is a conceptual understanding of unbiasedness, of standard errors. These concepts are not easy. These concepts are complicated. These concepts are indeed pretty mm, slightly difficult. So I'm glad that we've been able to get this through across clearly, and I would like you to revise them. I will now quickly take questions so that those of you who are wanting to leave can do so. Yeah. Okay. What about negative t statistics? Uh, that's fine. So Vandana, let me just show you. Let me just show you a t distribution. Okay. So then we'll just figure this out. Oops. Yeah. Okay. Yeah. Okay. So, Vandana, I'm responding to your question about negative t statistics. I'm very glad you asked because I wanted to show you something about hypothesis tests. Okay, so here on your screen, you have a t distribution. Okay. As I said, I really like labeling the axis. So what do I have on my axis? I have here varied values. Okay, so this has all the t values. And what do I have on the y-axis? On the y-axis, okay, I have the t density. So the t density, which you can see on your screen, is symmetric, and it is symmetric around 0. So I think many of you would have learned it in a preliminary statistics class that the t converges in distribution to the standard norm. So when the degrees of freedom of the t distribution becomes very large, it just becomes 1 with the standard normal distribution. And the standard normal distribution is centered at 0. The t is also therefore centered at 0. Now, what does that mean? You see, what that means is the following thing. It means that I can have both negative t values as well as positive t values. So all the variate values to the right of 0 will be positive, and all the variate values to the left of 0 is going to be negative, right? So look at our t-stat. What was our t-stat? How is it derived? Our t-stat is basically beta hat upon the standard error of beta hat, right? Now, what is the standard error? The standard error is a positive square root. It's a positive square root of an estimated variance, so it can never be negative. So the denominator is always positive. But what about beta hat? Beta hat can be negative also, right? So the sign of your t-stat will basically be given by the sign of your beta hat. Okay, so if your beta hat is negative, then you'll get a negative value of the t-stat. What does that mean? Always visualize. Once you visualize, you see, you can understand better. I at least find that. So you see, when you have a negative beta hat, you will see that your t value is negative and it lies to this side. So if you're doing a hypothesis test, okay, then you can see again in my diagram that for a hypothesis test to be done at the 5% level of significance, what does that mean? When I'm doing a two-tailed test at the 5% level, my critical region is equally distributed on both the tails, with 2.5% this side and 2.5% this side, right? So if you have a negative t-stat, then your critical value is really minus 2.06. This is at the 5% level of significance, t with 25 degrees of freedom. Okay. The critical values are marked on your screen. It is 2.06 on the right and minus 2.06 on the left. What that means is 2.5% probability lies to the right of 2.06, 2.5% probability lies to the left of minus 2.06, because the t is symmetric distribution. So you see, when you have a negative t value, your rejection region is just this one. That's all. Okay. So then what you're going to see is whether the value is something like minus 1 point. So if it's minus 1 point something, then you're not rejecting, right? And if it's minus 3 point something, then you're rejecting, because that lies over here. So you compare the absolute magnitudes, or you just look at it diagrammatically. So Vandana, I hope that is answering your question. Ouch. So I hope that answers your question. Okay. Yes. Sagar, you're saying that T is 10.6, but P is 2.783. How can that be? Let me look at that. Okay. Let me look at that. Okay, Sagar, relief. Look at something right here. Sagar, look at this thing. Sorry. Look at this. Minus 22. Okay. So just let me point this out. So here you go. You see, whenever you have a very large number, Excel will cannot fit it into that small space. So it will give you these kinds of messages. So E minus 22 means this is 2.783 divided by 10 to the power 22. So it is a very small number, which is almost 0. So p-value is very low. So we are clearly rejecting the null, whether you're looking at t-statistics, whether you're looking at p-values. Okay. I hope that takes care of your query. Right. So where did that query box go? Okay. Yeah. Okay. Now. Yeah.
Hi, ma'am.
Hi.
Hi, I'm Dr. Abha Vajpa.
Hi, Abha. Sorry, I asked you to switch off your audio then.
No, it's okay. It's perfectly all right.
Yeah, please tell me.
I was there for your class, and I think you've answered quite a few of the questions, queries. There were one or two technical.
Abha ma'am, आपका video नहीं दिख रहा.
वीडियो मैंने शायद खोला नहीं है.
खोलिए मैम प्लीज.
अच्छा खोलती हूँ, 1 मिनट होल्ड करो. अच्छा. So I think there was some little technical hitches in the thing. The one or two people were saying they were not, you were not audible.
अच्छा.
I think उनके end से ही problem होनी चाहिए.
Yes मैम, वो है. Can we have the questions मैम, अगर आपको लगता है कि कोई रह रहा है?
Questions,
I
there
just
are quite a few of them, and one or two people were getting, I think, too much confused.
अच्छा.
So I think when we'll send them the video and they will revisit the whole video, so
Okay.
they'll be able to get their queries clear. So
Okay.
if you can take up small questions, that's okay. Otherwise, we can wind up with the session and we can do it next week.
Okay, Shomik Chaudhary is asking. I'll just take up a few quick ones, okay?
Yeah.
That will be fine.
Shomik Chaudhary is asking, the intercept is not insignificant, is not significant. Should we? Yeah. So Shomik, don't bother about the intercept, but don't throw it. That is my request to you. Even if the intercept is insignificant, keep it there. It serves a very important role. Okay. So don't worry about it. It's just telling you that actually a line is through the origin. Yeah. That's all. Okay. For testing OLS regression model, do we always use t-test? Yes, we use a t-test to test the beta equal to 0, etc. If beta is negative, then critical value, I think I answered that question. If beta is negative, we look at critical values to the left of the t-distribution. Thank you, Del. You think I beautifully explained something. How nice of you to say so. What is the meaning of proxy error? I'm not sure. I don't know what is proxy error. Maybe what I was trying to tell you is the residuals are proxying for the errors. That's so not proxy error. The residuals are proxying the errors. They're estimating the errors. Saida, I hope interpretation of t-values is clear. If not, we'll have more on them tomorrow. Okay. Sonu Madan, thank you Sonu for saying the explanation is nice. When you learned it all lately or during your studies? You have made it too complex. Yeah. Anonymous attendee who thinks it's complex, these are complex. I'm not making them complex. They're very complex. So if you think you're walking into something simple, ha to you. These are very complex things. So let's wake up to that. Okay. Right. Okay. So I think that kind of takes care of stuff. Okay. I will tell you about Vijendra Pandey, Dr. Vijendra Pandey. I will talk about the Dastidar square tomorrow. Okay? Ankita, thank you so much. Thank you so much. How is the degree of freedom for regression shown as 1? It is not 1. Sorry, that's not 1. Huh? The degrees of freedom is what they are showing as residual. The other 524. What you are seeing is a ANOVA table. Okay? So don't worry. That is not degrees of freedom. Okay? Okay. Okay. Thank you. Thank you.